In this presentation, I'm just going to walk through some of the steps that you need to prepare your data, where you can get some of that data that you'll use in AGWA, and then also some tips and best practices for where you store your data and kind of what's going on behind the scenes with some of the data that we create. So our basic data requirements are a digital elevation model, your DEM. Any raster format that you can load into ArcMap will work. For soil, we accept GNATSCO, GSurgo, Surgo, StatsGo, and FAO soils. For land use, we out of the box accept the National Land Cover Dataset, and we also support user-defined land cover as long as it's classified. More on that in a minute. You need to know where you're modeling, so you need to have a pour point to represent your watershed outlet. That does not have to be in an actual gauge. You can put that anywhere in your watershed or anywhere on a channel. You also need precipitation data, and you'll also potentially want to use your hydrologic unit maps to clip your data. I do see in the chat that there's a few people who are having trouble with sound. I'm using two laptops. I've got sound coming from one computer and the presentation coming from another, so I'm not sure if that could be causing some of the issues, but I see that some people can hear, so I'm not sure what's going on with the people who cannot. But I'm going to keep going because it seems like most of you can. Anyway, first step is deciding where you want to model. It's locating your watershed. It's pretty basic, but important. Next step after you've identified the watershed that you're interested in is gathering the data for that watershed. In the US, you'll be using probably the national map to download your DEMs. I can't remember the service that I believe is run by the USGS that has international DEMs on it, global DEMs, but I should add that link later. Apologies for not including it here. For soils data, you'll either be using Surgo or StatsGo, which you can obtain from the Web Soil Survey or the USDA NRCS Geospatial Gateway. Or you'll be using GNATSCO and GSurgo. So those are the newer gridded products representing Surgo. And for GNATSCO, that's a continuous national database that combines Surgo, StatsGo, and web soil surveys. No, raster soil surveys. And then finally, for international applications, you can use FAO data. For land cover, National Land Cover Dataset is likely what you'll be using in the US. There's a couple different places you can download that. You will also support the USGS GAP data. I don't have it listed here. I think Phil will talk about it later. It's not directly supported yet, but the USGS land fire data set is also something that we're working on incorporating more directly to have better cover estimates instead of using average cover for classified land cover types, we would be using measured cover directly from the data in Landfire. So gathering data for KNRS-2 and for REM precipitation typically involves either design storms, which you can obtain from the NOAA Precipitation Frequency Data Server. You can also just input a storm depth and duration directly and have AGWA disaggregate that into a number of different rainfall distributions. You can input a user-defined hyetograph for observed events, or even a hyetograph for a synthetic event that would be, again, akin to a design storm. And then we also have a flash flood forecasting version of KNRS that uses radar data and near real time models those updated radar scans and is used for flash flood forecasting. We can also look at archived or historic radar maps to run old events. For SWAT, we need daily rainfall. You can obtain daily rainfall totals from a number of different places. The NOAA National Centers for Environmental Information, NCDC. DayMet will also give you daily values. And the easiest way to get your first simulation without having to go and download SWAT daily rainfall data is to just use the weather generator that's built into SWAT and pick the closest weather station or climate station to your watershed. So one of the first steps after you've downloaded all your data is projecting it all into the same projected coordinate system. There's a little nuance here where there's also geographic coordinate systems where you can have your GCS defined, and that could be NAD in 1983, it could be WGS 84. That's simply a geographic coordinate system. That's not actually projected data. So even though the application knows where you are because you have a geographic coordinate system defined for your data, if that's all you have, you must also project that. And you must choose a projection that has units in meters. Most state plane projections are in feet, and all of our calculations in AGWA are based on, or assuming that units are in meters. So if you use a state plane coordinate system that's in feet, those calculations are going to be wrong. So after you've obtained your data and you've projected it, a lot of times the DEMs that you download, for example, or even the soil data sets that you get may be quite a bit larger than the watershed that you're interested in modeling. So at that point, one of the things that we'd recommend is using the HUC watershed maps or some other representation of your watershed prior to you having delineated it in AGWA. Just take that and then buffer it out maybe a kilometer so that you have this nice buffer to clip all the data that you downloaded with. And then when you do that, you'll be working with a smaller sized data sets for your DEM, your land cover, your soils, which are easier to manage, reduces processing time, reduces storage requirements. So if you're interested in some of that, that will be gone over in the third tutorial. So Surgo and StatsGo data, there's two parts to that. There's the spatial data that has the soil mapping units. It's polygon feature class. That's what we intersect our watersheds with. But then associated with each one of those mapping units is the tabular data that has the properties for the different components, for the different horizons, and for the textures that those mapping units represent. And that tabular data for Sorgo and StatsGo, it's in a different separate access database. And when you download that data, it typically is just in a tabular folder, and you have an access database template that's provided with it that is empty. And you must import that tabular data into that access database. So we'll walk through that on the next slide. With Sorgo, this is an improvement over Sorgo and StatsGo. When we're not using it in this training, it's available in the next version of AGWA, which will be 3.11. In this training, we're using 3.10. So check our website over the next week or two for that newer version if you're interested in using Sorgo. But the great thing about Sorgo and GNATSGo is the spatial and the tabular data are delivered in one file geodatabase. So you don't have to worry about that second tabular part that you do in Sorgo and StatsGo. And when you select a Sorgo soils layer, AGWA will automatically select the appropriate tabular data from that file geodatabase. So it's kind of just a little bit, one less step that you have to worry about. And then with the FAO data, that's usable as is when you download it, because we've included the tabular data and the AGWA data files directory. So this is just kind of an animation of how to populate the soils database that you use for Sorgo and StatsGo. This is the typical layout that you'll see once you've downloaded that data. You've got the access database there called soildb_us_2003. When you download that, that's going to be empty. So you'll double click on it to open it in Access. When you open it in Access, typically you'll see the security warning across the banner at the top, where you'll need to click Stop All Macros in the pop-up, and then click on Enable Content in that banner. And when you do that, the first form that pops up is the import screen. And from there, you'll paste in the path to the tabular data that came in the download that's in the same path as this access database. And then once the import is finished, you'll see this soil report screen pop up. And at that point, you can exit the soil reports window and then exit the database. SWAT precipitation, you'll need a rain gauge point theme so that we can intersect that rain gauge or multiple rain gauges with your watershed. If you do have multiple gauges, then we'll use Thiessen polygons to weight the gauges and distribute the rainfall spatially across the watershed. You'll also need an unweighted precipitation file. So this unweighted file contains daily tabular data for each rain gauge that you intersect with your watershed. The formatting requirements are simply that it has the gauge ID that's in the rain gauge point theme. Because gauge IDs are normally numeric, and with some tabular data sets, you can't have fields that start with a number. Our requirement is that you put a G in front of the gauge ID for it to be recognized as an unweighted precipitation file in AGWA. You'll also need a year and then the Julian day of the year. And in that, and then under the gauge ID field is where the actual precipitation amounts are. So the year and the day are self-explanatory. Recommend that we have multiple years of data. SWAT typically has a spin up time for the model to get stabilized, water balances to kind of to stabilize. So you want enough data in there for that to happen, and then for you to be able to capture any climate trends and just the rest of your precipitation regime. And then if you have missing data, missing days in that unweighted precipitation file, those should be filled in with a -99, and then the SWAT weather generator will kick in and decide whether there's actual rainfall on that day or not. Getting to some best practices for working with your data. It may seem obvious to some, but maybe it isn't to others. It's a good idea to keep your input and your output data separate. I think it'll just be easier in the long run to manage your data, to find it, and to not accidentally erase it or change it in any way. So I typically have an inputs folder and then a workspace or an outputs folder that sit below where I store my ArcMap document for a particular project. So that's my recommendation after having used AGWA and working in GIS and modeling for 15 years. If you are familiar with ArcMap, you may like to go in and change certain settings for your project. We try to accommodate that as much as possible, but one thing that we still do require is that if you go in and change your geoprocessing environment settings, that your current and your Scratch workspaces must remain as file geodatabases and not any other type of workspace. I like to save my map document in my project folder. It allows me to easily use the catalog pane in ArcMap to get to my inputs and outputs data sets using that home button that I've got circled in the screenshot there. If I have my map document in that project folder, and then I have my derived outputs sitting below that and my inputs also sitting in that folder, clicking that home button will quickly take me to where I've got all of my project data. So that's something that I've found helpful. Another recommendation is be descriptive with the names for your data, for your delineations, discretizations, your parameterizations. In this example here on the right, did not do such a good job at that. You'll see a D1 and D2, and really that's like, what the heck do those mean? And they meant delineation 1 and delineation 2, but you could be a lot more descriptive than that. And it's really helpful if you have to go back and look at a project a year or two later, if you've got some descriptive names for data delineations, discretizations, parameterizations. And also, if you have notes, it's really good to be able to figure out what you did. So this slide shows some of the generated outputs that AGWA creates. When you do an AGWA delineation, it creates a personal geodatabase that contains your watershed delineation feature class inside that geodatabase. And then any subsequent steps that you perform using that delineation, that data will be stored in that geodatabase and in folders named according to that geodatabase. So when you create a discretization, it's going to create a polygon and polyline feature class representing the hill slope and subwatershed and stream model elements, and those are going to be saved in that geodatabase. And I don't know if we've done a good job, there's my mouse, talking about the discretizations yet, but basically that's that's subdividing your watershed into distinct model elements of hill slopes and streams. And then that's what the model actually runs on. When you create a parameterization, so you parameterize one of those discretizations with your land cover and your soils, that data gets stored in parameterization lookup tables, again, that reside in that personal geodatabase. When we create precipitation files, those are flat files that are read directly by the model, and we place those in a precipitation folder that's a subfolder of the discretization, which is a subfolder of the name of the delineation you created. So again, in this example on the right, we create a delineation called D1. And then inside that D1 delineation, we create a discretization that was named D1S1. That's not shown. I should have expanded the D1 geodatabase here to show that. But if you were to expand it, you would see a D1S1. And you would also see the parameterization lookup tables in that D1 geodatabase right here. When you create the precipitation files, that's when we are storing things as flat files. It's basically text files that get organized according to your delineation name, the discretization that the precipitation files were written for. And then finally, when we do a simulation, that's creating the model input files, which are also text files. And those get placed in the simulations directory.